In this week, we're going to go through Chapter 6, Current, Resistance, and Circuits. This is going to serve as the final chapter for the electricity portion of our E&M course. The next chapter is going to talk about and introduce us to magnetism. So as a summary of all of the different electricity topics that we've talked about, we're now going to try and summarize everything and discuss what is included in primarily circuits and how we can analyze different components of circuits and how they're applied to real life. Okay, as the final chapter of the electricity portion of this course, this topic is going to be fairly lengthy. The first thing I want to do is go through a recap from the previous chapter, which is capacitance. And because this chapter builds directly upon that chapter, we're then going to move on to current density, then talk about another component within circuits called resistors, talk about resistivity and Ohm's law. Afterwards, once we know about capacitance and resistors, we can take a look at the electric power and electromotive force that powers the circuit. And then, of course, go through an overview of DC circuits in its entirety, from circuit diagrams, resistors, different measuring instruments that are used in circuits, the laws that define different loops and junctions called Kirchhoff's laws within those circuits, and then take a look at circuits with both resistors and capacitors called RC circuits. Once we have all of that knowledge, we'll be able to apply them to different models and techniques within biophysics and medicine. So that would be, for biophysics, the Hodgkin-Huxley model for membrane current. So we can actually mimic a membrane or a biological membrane as a circuit. Next, for real-life applications, we can use voltage clamp experiments to test membrane voltages from one side to another through different methods like the patch clamp technique. So these are things that we are going to go through. And of course, circuits are everywhere nowadays. There are so many electronic devices used in medicine that each of them will require a circuit. And the more complicated your device is and the more features and functionalities that it has, the more complex the circuit will be. Okay, so let's go through a quick overview of capacitance. So mainly, what is capacitance? What are the main equations related to a capacitance, as well as what kind of energy can be stored in capacitors? So the key equations we looked at in the previous chapter that will be useful for this chapter would be the equation for capacitance, which is C equals Q over V, or epsilon naught A over D if we know the area of the plate, as well as the distance of separation distance between the plates. One important concept to understand is the difference between putting capacitors together in parallel or in series, because when we talk about resistors, the trend will be reversed. So with capacitors, if you set them up in parallel, in which case you have the same wire being split into multiple parallel capacitors, or the wire being split and then connecting different capacitors in parallel to each other, and then also having the wire come back together at the end, so you have the same wire at the top and the bottom. That is a capacitance in parallel. When you're trying to calculate the equivalent capacitance, you're just adding up all the capacitors and their capacitances together to get the total capacitance. Now, if you had a chain of capacitors, so you have one wire and then it's connected to one capacitor and then connected to another one and another one, that is called a capacitor in series. And so when you have something like that, then the equivalent capacitance is calculated by adding up the inverse or the reciprocal of all of those individual capacitances. Next, you have capacitance with dielectrics. And with the dielectric, you have the dielectric constant kappa that's introduced because it is just a factor of the original capacitance. You have the work to charge a capacitor defined as 1/2 of CV squared. And because of this, you can also define work as the potential energy that's stored within the capacitor. And you have the same equation, but when you introduce C equals Q over V, you can rearrange this into various different formats. Now, the last one, we talked about electricity energy density in a vacuum. So basically, there are two different views of looking at electric energy. You can take a look at it from a physical perspective, or you can take a look at it from the electric field perspective. So from that electric field perspective, we are able to calculate how much energy is within a certain region of an electric field at a certain point in time. So over here, we have U equals to 1/2 epsilon naught E squared to let us know how much energy is stored within a specific area of that electric field over here. And then if you want to get the total electric energy stored in the entire shaded volume, all you have to do is integrate that equation for U. Now, moving on to electric current and circuits. So we're going to go through the big picture and why it's important to understand these. So first of all, what is an electric current? It's the flow of electric charge with its microscopic entity called current density. Now, something very important to understand is when we're taking a look at current, you can have a microscopic view of current and you can also have a macroscopic view of current. The macroscopic view of current is something that we should all be familiar with already. That's the equation with the V, the I, and the R. So those things are macroscopic because they're qualitative observations that we can make as well as measurements that we can take. Now, for the electric current, there's also a microscopic component to it, and that's called the current density. How much current can a specific portion of that object carry at a certain point in time? So those are two things we're going to take a look at, starting with the microscopic. Ohm's law is not a fundamental law, but it's very important in relating current and voltage, or the microscopic view would be density and field. So at some point, we're going to define the differences between the microscopic and macroscopic views of Ohm's law. Now, for the electric circuit, that is a network of different electrical components like capacitors, your wires, as well as your current and your resistors. That includes one or more sources of electric energy. So throughout this whole chapter, we're going to learn a lot. We're going to learn about resistors and capacitors and their uses within circuits. We're going to learn about the electromotive force, or EMF, and we're going to learn about Kirchhoff's rules that define different points within the circuit. So why study electric current and why is it important? So far, it's important to note that we have only studied the interactions of electric charges at rest. We haven't really studied what happens when those electric charges move. And as soon as they move, then that means that there's going to be a current. And so when we want to look at moving charges, we want to take a look at charges that follow a closed conducting loop called an electric circuit. So that's kind of the definition of that. The purpose of an electric circuit is to transfer energy from one place to another. So it can be used for many different types of electronics or battery-powered devices because they have sources of electric energy. So from a simple flashlight to complex computers to operating an MRI machine, these are all different applications of electric circuits that we may not necessarily go through in detail, but we'll go through in general what kinds of applications are typical for electric circuits. Now, going back to the electric current, an electric current represents the flow of charge or the net rate of charge crossing an area. So if you're taking a look at an object and you're looking at charges in motion, you're taking a look at one point at the beginning or one section of the object and another point at another section, maybe the end section of the object, seeing how much charge goes from point A to point B, and especially how large the cross-sectional area is for the charge to move through. So knowing that gives us electric current. Its units are coulombs per second because it is a rate how much charge flows through a specific cross-sectional area in a specific amount of time from point A to point B. So coulombs per second is also known as amperes, or just A. And it's named after a French physicist called André-Marie Ampère. from 1775 to 1836. So brief little blurb about him. Okay, so let's move on to current and current density. So we're first going to go through what a current is and how we can define that mathematically, take a look at current density, and then take a look at what conductivity means when we're looking at materials. So the first thing we want to discuss is the difference between different types of current. So even though we know electric current represents the flow of charge that crosses a specific cross-sectional area of your object, we still have to define it mathematically. So if we have a charge, delta Q, and it crosses a given area in a time, delta T, then we have a very simple definition of current, which we call a steady current. So that means everything is consistent. We have a certain change in charge over a certain change in time. Now, the problem is there are sometimes time-varying currents, and that means we have to take the limit of small time intervals. So you then have an instantaneous current, dq over dt. So main difference, you have something that's steady, it won't change, it's constant, you have delta q over delta t. In other cases, you have a time-varying current, in which case you can only take a small snapshot in time and see how much charge flows through within that specific period of time in that specific area within that object. Now, what is net current? Currents are in the direction of positive charge flow. So I've highlighted that because it's important to understand that is the typical convention. Wherever the positive charge is flowing, that's typically the direction of your current. If your moving charge is negative, then the current is going to be opposite of the motion of the charge. So very, very important to understand that when we are moving on to circuits and taking a look at current within circuits. So over here, there's a diagram. My positive charges are moving towards the right. It means that the current is moving towards the right. Now I take a look at my negative electrons. They're moving towards the left, but that is not a positive charge. It's a negative charge. So that means that our current is moving towards the right. It's very similar to how we have conventions with electric field as well, and how the electric fields always radiate out from a positive charge and in from a negative charge. So now we take a look at what happens if we have two different kinds of moving charges. So a little bit more complex. The net current is going to be the sum of the currents carried by the positive and the negative charges. So if you have some positive charges moving towards the right and some negative charges moving towards the right as well, then some of it's going to cancel each other out because you have your positive current towards the right, and then for the negative charges, if it's going towards the right, then you have a current flowing towards the left. So depending on how much there is of each and how fast each of the positive and negative charges move, you're going to get a net current. So if you have a neutral object with zero current, the assumption is that you have an equal number of positive charges and negative charges moving in the same direction, which means that the current is going towards the right and towards the left at equal magnitudes to cancel each other out. So that's this case over here. Now, I talked about the microscopic and macroscopic view before. We're now going to take a look at that starting from microscopic. So the macroscopic view is the one that most people are familiar with. It's the one that relates electric current and voltage. So that's really helpful to us when we're analyzing electric circuits. So if you're an engineer or somebody who's just dealing with the applications of electronic devices, you will most likely be dealing with the macroscopic view of circuits and currents. Now, the microscopic view describes the relationship between the electric field and current density at every single point within a conductor. So this is very useful when the electric fields are going to vary with each position. So whether you're in biophysics, astrophysics, or engineering, if you're designing electronics or if you're doing theoretical studies or modeling with circuits and different objects that can carry different current densities, then we're going to have to take a look at the microscopic view to understand the relationship between that object and its current density and its electric field. So we're going to start with the microscopic view of current. This current will basically depend on the speed of the charge carriers, their density, as well as the charge that they hold. So we're going to focus on conductors. In a typical conductor, the charges move about at very high speeds with random thermal velocities. And it's these random thermal velocities that we don't really care about. We realize that they don't result in a net flow of charge. When the currents are present, there is something else that we have to consider. It's called a drift velocity. So that drift velocity is superimposed on the random motion that the conductor and the charges have, and that results in a net flow or current. So just to summarize, in a typical conductor, you have charges that move about at a high speed with some random thermal motion. We don't care about the random thermal motion, but rather when a current is present, we care about the small drift velocity that comes with that random motion. And it's that small drift velocity with the random motion that results in your net current. So assuming a conductor has n charges per unit volume, so we take a look at a chunk of that conductor, or a chunk of a volume of that conductor. We say that it has n charges within that volume. Each chunk has a charge Q, and each chunk moves with a drift speed of Vd. So if we know the speed, the charge, and how many charges are per unit volume, then we can calculate the current. So we have to use some macroscopic quantities of cross-sectional area, like A, and the conductor length L, just so that we can calculate the volume portion, but the rest are microscopic. So outside of being able to figure out the volume of your conductor, or a partial volume of your conductor based on the cross-sectional area and the length of that volume, you have a total charge, delta Q, and you have a total time, delta T, because at the end of the day, we're calculating I equals to delta Q over delta T. But in order to figure out delta Q, we have to come up with an equation for that. Since we know the volume and we know there's going to be charge associated with it, then we know that we have a charge per unit volume, N, so N per unit volume, but that's just a number. We know that every charge N holds a charge Q. So the total amount of charge is going to be NQ per unit of volume. Because it's per unit of volume, we have to multiply by volume. So we end up with NQ times volume, which is AL. So we have NALQ as our delta Q. The total time, delta T, is going to be a value that we have to try and manipulate from our givens. So we know that there is a conductor length L, and we know there's a drift speed Vd. So if we have L over Vd, it will give us units of time. So we use L over Vd as our change in time. So based on that, we can summarize everything and put together an equation known as the microscopic current, defined by small changes within a volume of the conductor that we have. So we have I equals to delta Q over delta T. Our definitions replace these two, and we end up with NAQ Vd. So taking a look at this diagram, we have a cross-sectional area, doesn't have to be a cylinder, cross-sectional area of a certain length. There are n number of charges per unit of volume, each with a charge Q. So keep in mind, n is just a number of charges, but each of them holds Q, so we have to have NQ times the volume here to get our total charge. And of course, all of these charges, we don't care about the random motion. We care about a general drift velocity where each of them could be vibrating, but also moving in one uniform direction, which we call and summarize as our net drift velocity. Now that we can calculate a microscopic current, we can calculate current density. So from that diagram that we had before, it kind of looks like we were looking at a wire, but it's not always going to be a wire or a simple object that we can look at. Currents can exist in large solutions, like chemical solutions. They can exist within our bodies. They can exist within gases, and their magnitudes and directions are going to change with position depending on what kind of object you're looking at. So it's important that we define a current density that is specific to different types of conductors and different shapes and applications. So we call the current density J, and it's defined as the amount of current flowing per unit of cross-sectional area, with the assumption that the direction, because it is a vector, the direction is that of the current. So to derive the equation, we have to divide our microscopic current by area. So keep in mind it is current density, so how much current per unit area. So we have I over A to define our current density. We simply have NAQ VD divided by A. The A cancels out, and we have a definition or an equation for current density known as NQVD. So now that we have a good understanding of current and current density, we then take a look at conductivity. So with moving charges, there is no electrostatic equilibrium. The field inside a conductor no longer has to be zero. So that's a very important thing to remember. Because there is no electrostatic equilibrium, and because the charges are moving, there is no guarantee that within a conductor you just have zero charge, because your charges are moving and there could be an electric field that's being generated. So because there is an electric field that's being generated within a conductor with moving charges, it is going to result in an electric current. So by Newton's law, the electric field should continuously accelerate free charges, resulting in an increasing current. But that's actually not the case. Charges are usually going to collide with ions and lose energy, and so this effective force is going to counter the electric force. So if there's a question about whether the electric field and the presence of an electric field should continuously accelerate free charges, then the answer is no. There will be no increase in current due to the generated electric field, because the charges are going to usually collide with each other and different ions and lose energy to prevent that from happening. So back to conductivity, we know that the electric field helps to sustain a steady current. And because field and current are in the same direction, we can now have a direct expression to relate the two of these quantities. And we actually just call this the microscopic Ohm's law, where we have J is equal to some sort of proportionality constant times E. They're in the same direction, so there's no negative sign or anything. There's just this sigma over here. And that sigma has to represent something. And if we're looking at current density J over here, and we have electric field, then sigma can pretty much represent the conductivity of the material. The more conductive the material is, the more the current density will be. So the more conductive a material, the more easily current can flow through it, and therefore the more conductive it is. So that would be the definition of Ohm's law from a microscopic perspective. Now, because we have conductivity, it means that we can have ohmic materials or non-ohmic materials. So basically those with high conductivity and those with low conductivity. So depending on what kind of material you have, if it's an ohmic material, they are going to be conductors whose conductivity sigma is independent of the electric field. Basically, whether it has high or low conductivity, usually high, the electric field will not affect this parameter. So current density and electric field are then linearly proportional based on the previous equation. When we're taking a look at non-ohmic materials, they are conductors where the conductivity does depend on the electric field, in which case the conductivity is going to decrease as well. So the relationship between current density and the electric field is therefore categorized as nonlinear, and that equation that we presented before will not be applicable to non-ohmic materials because it doesn't follow the microscopic view of Ohm's law. The first problem we want to go through is a current in a copper wire. So a 5 amp current flows in a copper wire with a cross-sectional area of 1 millimeter squared carried by electrons with number density 1.1 times 10 to the 29 meters to the negative 3. Find the electron's drift speed. So first, we want to either draw a diagram or state known values. So I'm going to keep it simple. We're going to write down our known values. Okay, so we're given the fact that we have I equals to 5.0 amps. We have N being equal to 1.1 times 10 to the 29 meters to the negative 3. We have a cross-sectional area of 1.0 millimeters squared equals to 10 to the negative 6 meters squared. And we have Q 1.6 times 10 to the negative 19 coulombs for each of those electrons. We also know that I, from the notes, is delta Q over delta T, and so it's going to be NAQ VD, where this is what we're trying to solve for. So we can directly solve. We have I equals to NAQ VD. We want to solve for VD, so it's going to be I over NAQ. This is then going to be 5.0 amps over N is 1.1 times 10 to the 29 meters to the negative 3, 10 to the negative 6 meters squared, and then 1.6 times 10 to the negative 19 coulombs. So that will give us VD is equal to 0.28, not meters, millimeters per second. Let's get rid of that. And that is our answer for your drift velocity. The next problem has to do with current density in membranes. So ion channels are narrow pores that allow ions to pass through cell membranes. Our particular channel has a circular cross-section of 0.15 nanometers in radius. So we can just assume that this has a cross-section with a radius of 0.15 nanometers. We're just going to assume that it has a circular cross-section. It opens for 1 millisecond and passes 1.1 times 10 to the 4 singly ionized potassium ions. Find the current and current density in the channel. So this sounds fun. First, we have to find the relevant equations that we have to use. We know, so let's just write down equations and givens. We know that current is the rate of charge passing through an area. So that means we know that I has to be equal to delta Q over delta T. Now the current density is the current per unit area. So current density is going to be J equals to I over A. What are some known values? We know that delta Q is equal to N times Q. We also know that delta T is equal to 1 times 10 to the negative 3 seconds. We know that N is 1.1 times 10 to the 4. And they're going to be singly ionized potassium ions. So that means Q should be equal to 1.6 times 10 to the negative 19 coulombs. Now for J, we know that I will be solved from I equals to delta Q over delta T. We know that A is the cross-sectional area for a circle, which is pi r squared. And we know that R is equal to 1.5 times 10 to the negative 10 meters. So based on that, we can start solving for each of these. Let's start off with I. I is equal to delta Q over delta T, which is equal to NQ. We know that N is going to be equal to 1.1 times 10 to the 4, 1.6 times 10 to the negative 19 coulombs divided by 1 times 10 to the negative 3 seconds. And so I is equal to 1.76 times 10 to the negative 12 amps, since it's coulombs per second. Okay, so next we want to figure out J. J is going to be equal to I over A. We already know what I is because we just solved for it. So it's 1.76 times 10 to the negative 12A. The area was pi r squared, so we have pi, and r was 1.5 times 10 to the negative 10 meters squared. And we end up with J equals to 2.49 times 10 to the 7 amps per meter squared. So that would be your answer for current density. So moving on, now that we've learned about conductivity and current, we want to move on to resistivity, resistance, and Ohm's law. So these are different concepts that are also important before we move on to circuits. So first of all, let's have a brief discussion about what the differences are between conductivity and resistivity. The conductivity sigma of a material, which we briefly talked about in the previous section, describes how easily charges can move through that material. So that means it will tell us how large the current density is going to be from the electric field, because J is equal to sigma E. A perfect conductor will have sigma equals infinity, as in the charge just freely flows through the object. And a perfect insulator would have sigma equals 0, as in no charge. Zero charge can flow through the object. So conductivity is a good measurement of how easily a charge can move through an object. Now, if we're taking a look at resistivity, well, we're just going to briefly describe what it means. Resistivity is going to be the opposite of conductivity. How resistant the material is to a charge moving within it. So in that case, we can just define resistivity rho as the reciprocal of conductivity. So that is the relationship between the two of these. Basically, when we're defining current density, we can use either one of these definitions, especially if we understand how they're related to each other. So the inverse of conductivity is resistivity, and that means the higher the resistivity, the lower the conductivity of the material, and the stronger the electric field required to produce a given current density. So as part of the microscopic view of Ohm's law, we can rewrite it as J equals to E over P. We basically replaced sigma with 1 over P, 1 over rho. So looking at the units of resistivity, they're going to be the inverse of conductivity. With the equation shown before, resistivity is going to be equal to the electric field divided by the current density. So that means the units are going to be voltmeters divided by amps, which we know as V over A. And we call that ohm. And that's why it's called Ohm's law, because we have a definition in order to derive the units based off of ohm. So the resistivities units are going to be ohm meters, because that will be how much resistance there is for a given measurement. So the range of values for conductivity and resistivity are going to vary immensely depending on the object that you have. And it's one of the broadest of ranges of any physical quantity. So essentially it spans over 24 orders of magnitude, and you pretty much need a chart or a table like one of these in order to determine what the resistivity is. So one thing to note when we're taking a look at these tables and graphs, you'll note that the resistivity of materials is given as ohm meters. And this is something that's very common in materials. So in materials, we do take a look at resistivity over conductivity. And most of the information that's given on packaging, as well as different labels, they would be given as ohm meters. So taking a look at this, for conductors, it makes sense that the resistivity would be low because they are good conductors of, especially metals. They're good conductors, so we expect the resistivity to be low. Now, if you have more combinations of different types of metals, like such as alloys, then your resistivity might increase because there are more components within that conductor. Moving on, you have semiconductors, such as silicon and carbon. And that resistivity is going to now increase. So it's less conductive, more resistive. Then after semiconductors, we're going to talk about semiconductors as well separately because they're quite unique. Moving away from semiconductors, we have insulators. And so it's expected when we take a look at insulators that the conductivity is going to be low, so less charges are going to move throughout the insulators, and therefore the resistivity will be high because it's going to try and prevent charge from moving through. So wood is one of the highest, insulators with the highest resistivity, so charge is going to have a lot of difficulty moving through wood versus amber or glass. So now we want to take a look at conduction in metals. Why are metals good conductors? So based on that table that we looked at before, we saw that the resistivity was very low for metal conductors. And the reason for that is because many free electrons are going to respond very well to electric fields. So in a crystal lattice structure like this, free electrons are going to move around at speeds of 10 to the 6 meters per second, and they're going to collide with ions or surrounding ions and bounce off in different directions for random motion. So that's already how it acts naturally. There is no current involved because it's just random motion, but when we do introduce an electric field, then there will be current involved, and therefore we have to take a look at its conduction. So over here, we have a bunch of positive charges and we have a negative charge here. The assumption is that negative charge bounces around all over the place. So introducing an electric field is going to accelerate electrons in the direction opposite of the field. So the electric field is going towards the left. Drift velocity is then going to be added to the random thermal velocity due to collisions. So there is going to be some sort of drift velocity involved. And when we talk about current, just like we defined before, our current is going to be proportional to the drift velocity. So then we have to look at what affects the drift velocity. If we introduce an electric field and we know that the drift velocity is going to affect and define the magnitude of our current, we have to look at what defines drift velocity. And it's going to depend on the electron's acceleration and the rate at which they undergo collisions. So moving forward, let's take a look at ohmic materials. Why are metals considered ohmic materials? We have to do a comparison of thermal motion and drift velocity. So any additional drift velocity makes no difference in the collision rate. So the collision rate is always going to be constant. So when we take a look at ohmic materials, we have to take a look at the drift velocity and the current and know that they are both proportional to the electric field. It means that there's going to be a direct proportionality between current density and field, which we already know, J is equal to sigma E, or J is equal to E over rho for resistivity. And so metal conductivity is then going to be linearly dependent on temperature, because we're trying to figure out what causes a change in the collision rate. So metal conductivity is going to increase with higher temperatures, because higher temperatures are going to increase the collision rate, they're going to decrease conductivity, and they're going to increase resistivity. So let's go through each of these and explain why it's happening, because there are quite a few terms that you'll have to wrap your head around. So with higher temperatures, you're going to increase collision rates. Now, the problem is when you're increasing collision rates, it has no difference in the drift velocity. And because there is more movement and more thermal motion, which doesn't affect drift velocity, the conductivity is going to decrease. And because the conductivity is the inverse of resistivity, the resistivity will increase. So just keep in mind, as you increase temperature, you are going to increase collision rates, but you're not going to increase conductivity, because you're taking away, you're adding more random thermal motion to the material. So just looking at this, because temperature does affect metals' conductivity, we have to take a look at thermal noise. If we introduce thermal noise to a material, even if it's localized thermal noise, it's going to affect the current at that position. There's going to be random fluctuations in the current's magnitude and direction, and that is why overheating an electronic device or an electronic equipment that's sensitive to heat, that is going to cause a lot of noise in the current. So whether you have computers, or whether you have a tablet or a phone, or even some sort of interface that's controlling a large device, we usually try to cool a device so that we can reduce the thermal noise for our applications. Next, we want to take a look at ionic solutions. So liquid solutions can have both positive and negative ions, and they must respond to an electric field. So that means even if you're taking a look at a liquid ionic solution, you can still have a net current. But we have to agree that ionic solutions are not metals, and they're not the best conductors. So that is because their conductivity is going to be limited by the natural collisions that take place between ions and neutral atoms. Okay, so moving on to plasma. Plasma is ionized gas, and for some, it's considered one of the 4 fundamental states. It was first described by the chemist Irving Langmuir, who was a pioneer in surface chemistry. So that was back in the 1920s or 1930s. So usually you have solid states of matter, you have liquid, then gas, and then you have plasma, which is ionized gas. So that's the 4th level that usually we don't consider when we're talking a lot about the fundamental states. But it's the 4th one, and it comprises of free electrons and ions, which makes it very electrically conductive. So a lot of energy is required to ionize atoms, so they usually exist at high temperatures only. So how are they made? Basically, we have to heat neutral gas or subject it to a very strong electromagnetic field until it becomes electrically conductive. Plasma dynamics are therefore going to be a lot more sensitive than neutral gas, and their behavior is going to be dominated by electromagnetic fields from a long-range perspective. So this is something that we won't really touch base on too much in the future, but it's just something to know about. Semiconductors. I had mentioned before that semiconductors are very unique, and so we do have a few slides dedicated to semiconductors. In some insulators, there are random thermal motions that can dislodge a few electrons. So it's very important to know this because even though you have an insulator, there is an opportunity for them to conduct charge and for the material to have some conductivity. And that's why semiconductors are not really insulators and can't really be categorized just as insulators. They mainly have properties of insulators, but depending on their thermal motions, you can have dislodged electrons that give them qualities of a conductor. So that's why they're called semiconductors. For semiconductors, they're both good insulators and good conductors with the condition that some of the electrons get dislodged. What happens is over here, we take a look, there's a hole over here and there's an electron over here. So we're going to describe what has happened. First of all, the electron isn't supposed to be here. It was supposed to be here in this hole. When it's dislodged over here, due to thermal motion, it's going to leave a hole where other adjacent electrons can fall into. And that's usually given a nudge by your electric field that's present within your object. The holes are then considered positive carriers and they move in the direction of the electric field. So the electrons and the holes, so both the electron and the hole, are going to move in opposite directions, and that is going to create an electric current, because if the electron is moving in one direction, then the electric field of the current is going to flow in that direction. If the negative charge or the electron is moving in the opposite direction, then the current is going to flow in the opposite direction, in the same direction as the positive charge. So they double up and create an electric current. Now, there's also something else we have to consider, and it's called doping. A key part to semiconductor technology is the fact that you can dope the material with impurities that will alter its conductivity intrinsically. So, can we shift the balance of charge carriers is the main question when we're taking a look at doping. If we can add atoms with more negative charge carriers, like phosphorus, then we have an N-type semiconductor. If we can add atoms that leave extra holes, like boron, we call this a P-type semiconductor. So taking a look at phosphorus, this is the structure of phosphorus with 5 valence electrons. So over here, the phosphorus can fit into a silicone structure, but is going to leave an extra free electron over here. And because of that extra free electron, you can alter the conductivity of the material whenever you introduce an electric field. So now that we know there's P-type and N-type semiconductors, we take a look at what we call PN junctions. A PN junction is the most important part of any semiconductor because it allows us to easily switch the conductivity on or off depending on what kind of material you have from one region to another. So let's explain these 3 diagrams. The first one over here, there's a P section, there's an N section, and we have this what we call a depletion region. So at first, with no battery, the electron and holes are going to diffuse across the junction. So they're going to recombine. So let's just start. With no battery, The electrons and the holes are going to diffuse across your junction and recombine, depleting the area of charge carriers and making it a poor conductor. So that area will not be a good conducting region. Now, in the next step, we attach both ends of the PN junction to a battery. If we apply a voltage from the P to the N region, it lets charge flow through the junction over here. And the other way will not work because it only conducts in one direction. And that is one of the key things to these PN junctions. It only works in one direction. So connecting the battery like this pulls the electrons and holes away from the junction, and the depletion region is going to widen and little current will flow. Now, in the next section, we have the battery driving the charge carriers to the junction region, permitting the current to flow. So first you have a depletion region, you attach a battery, which expands the depletion region, and as that battery continues, the battery is going to drive the charge from the P to the N direction. So that summarizes everything in terms of the microscopic view of current. We now want to move on to the macroscopic view of Ohm's law and the macroscopic view of current. So this is the one that we should all be most familiar with. Ohm's law states that the current through an object is going to be proportional to the voltage across it and inversely proportional to the object's resistance. So this is a good continuation of our discussion off of PN junctions because we've now attached a battery and we've introduced some sort of voltage. So resistance versus resistivity, they both start with the same word, so it should mean that they're both related. Resistance should be related to resistivity, which is defined as E over J, and we know J is equal to I over A. So combining all of this, we know that resistivity is EA over I. But, oops, this part is cut off. We also know that V is equal to EL from our discussions of potential. So we can rewrite this as rho equals to VA over LI, or V is equal to rho LI over A. So that there's an I that's cut off over here. So taking a look at the diagram here, you have a potential difference between point A and point B at the other end of this current carrying wire. Current is going to flow from the higher potential to the lower potential across a distance L. Now, you also have a current defined as I, you have the electric field pointing in the same direction, and you also have the current density not current density, you also have the current current density J flowing in the same direction. So that gives you a good idea as to the flow of current through an object from higher to lower potential. Now from that equation, because V equals to I over R, we can rewrite everything and say the resistance is equal to resistivity times L over A. And that is going to be the connection and the relationship between those two parameters. Now, there's an alternate way of writing Ohm's law. Instead of I equals to V over R, you can write V equals IR. That's probably the most common form that you'll see. And we didn't really have to go through it that much. It's a very simple equation. So now we can have a comparison chart between the microscopic and macroscopic views of Ohm's law and the different parameters within. So let's go through a comparison. We have the microscopic view of the electric field, and E is defined at each point in a material. But when we're looking at the macroscopic view, we don't look at the electric field anymore. We look at the integral of the electric field over a path, which is known as V, because V is equal to EL. So what is the condition for a macroscopic view? It's the fact that we should probably have a uniform field in order to define what the voltage is. Next, you have microscopic view. We did take a look at current density instead of current. Oh, and that's actually I, not J. J is defined at each point within a material, where I is the integral of J over an area. So please change this to I. Just gonna do a little, should be I. Okay, so we know that if you have uniform current density J, then you have I equals to J times A. So keep in mind, so far we've found out that with the macroscopic view, we know that the electric field is uniform, so that we can have voltage. We know that current density must be uniform so that we can have current. We have resistivity rho, and if it's uniform, and there's a uniform cross-section, we get resistance R. And so we have the microscopic view of Ohm's law, where everything is not consistent and not uniform, and we can calculate the current density. And we have the macroscopic view of Ohm's law, in which case it relates current through to voltage across a given piece of material. In problem 3, we want to take a look at household wiring. So a 1.8 millimeter diameter copper wire carries 15 amps to a household appliance. We're trying to find the magnitude of the electric field within the wire. We're given the fact that the resistivity for copper is 1.68 times 10 to the negative 8 ohm meters. So first, state our known values. Or at least what's given to us. We have I being equal to 15 amps. We have the resistivity as 1.68 times 10 to the negative 8 ohm meters. We have a cross-sectional area of pi r squared, which is going to be pi, and then we have a diameter of 1.8 millimeters, so 1.8 times 10 to the negative 3 meters, divided by 2 squared. We have J being equal to E over P. These two are vectors, just keep that in mind. But we also know that J is equal to I over A. So that means E is equal to I rho over A. Now just keep in mind this is not P, it's rho. So next we just solve. We have E, and we're just trying to find the magnitude, so we don't even need a direction. E is equal to I rho over A. It's equal to 15 amps multiplied by 1.68 times 10 to the negative 8 ohm meters divided by, that. So it's going to be divide pi 1.8 times 10 to the negative 3 meters squared divided by 2 squared, which is 4, and we can just put that up at the top. We should be able to get E equals to 0.099 volts per meter, which we can simplify to 99 millivolts per meter. So that would be the magnitude of the electric field within the wire. Now let's take a look at starting a car. A copper wire, 0.50 centimeters in diameter and 70 centimeters long, connects your car's battery to the starter motor. What is the wire's resistance? And if the starter motor draws a current of 170 amps, what is the potential difference across the wire? Assume that the resistivity for copper is 1.68 times 10 to the negative 8 ohm meters. So once again, I'm going to state all of our known values so that we know what equations we should probably use. Copper wire is 0.005 meters in diameter, so R is going to be 1/2 of that, 0.0025 meters. Now we have the length, which is 70 centimeters long, or 0.7 meters. I'm always trying to change the SI units if I can. I is equal to 170 amps. We have no idea what V is, and that's what we're trying to find. Rho is 1.68 times 10 to the negative 8 ohm meter. We know V is equal to IR, and we know R is equal to rho L over A. So first is to find resistance, R, and that's going to be equal to rho L over A, which we should be able to solve easily. L is 0.7 meters. So up at the top, we already have meters squared. A is then going to be pi 0.0025 meters squared. And that gives us 0.599 milliohms. So that's the resistance. Next, we want to figure out the potential difference. So V is equal to IR. So that's simple enough. We have 170 amps multiplied by 0.599 times 10 to the negative 3 ohms. And we end up with 0.10 volts as our potential difference. So now let's move on to electric power and electromotive force. We've now learned about capacitance from the previous chapter. We now know about current and resistivity. And we now want to take a look at how to calculate different components of electric power, and then move on to circuit components. So electric power refers to the power that's dissipated in heating a resistor, or the energy per unit time. It's the product of the energy per unit of charge and the rate at which the charge moves through the conductor. We call electric power the number of watts in a system, so it's going to be 1 joule per second. So electric power is defined as P equals to IV, or P equals I squared R, or P equals V squared over R. Depends on how you want to integrate Ohm's law into this equation. Now, let's take a look at what happens if you have high voltage. Everyone knows that high voltage is probably unsafe, but we should probably figure out why. It's actually not the voltage itself, but the current that goes through the human body that can kill us. So depending on what kind of current you have, it could be very dangerous. If you have 0.5 to 2 milliamps of current, then the effect is really just the threshold of sensation. So within this range, you'll feel a slight shock, but it won't really do any damage. Now, if you go up to 10 to 15 milliamps, you have involuntary muscle contractions, in which case, if you get shocked, you'll be frozen in place and partially paralyzed. You won't be able to let go because your muscles have involuntarily contracted. Now, from 15 to 100 milliamps, you do get a severe shock. Muscle control is lost, and you have difficulties in breathing because, once again, your body is a conductor, and so therefore that charge is going to, and the current is going to go through your whole body. Now, from 100 to 200 milliamps, you're going to get a fibrillation of the heart, and therefore death within minutes. And this is where defibrillators are going to commonly exist in terms of how much current and electric shock is delivered to your body to restart your heart. So over 200 milliamps, you get cardiac arrest, your breathing is going to stop, and you get severe burns, depending on where the entry and exit point of the current is. So focusing more on how electricity affects the human body, when an electric current enters the body, it's going to enter through skin contact. So our skin, our sweat, the oils on our skin, these are all conductors. And so the primary external danger is the disturbance of the electrical activity of the heart. Because we are conductors through our skin, when an electric current enters the body, our biggest fear is that it's going to travel to our heart and cause a cardiac arrest. So the internal lethal zone is much lower, though, if you want to cause any damage, even though you can cause a heart attack with greater magnitudes of current. Internal damage is possible at lower amps as well. So we take a look at fibrillation between 100 and 200 milliamps, and we think about why defibrillators even work. Now, defibrillators aren't going to immediately kill you, but defibrillators have the same effect. They're going to deliver an electric shock to your body so that it can jumpstart the heart based off of this lethal zone of 100 to 200 milliamps. They usually apply a high enough current to stop the heart. And once the heart is stopped, then hopefully it has enough power to restart normal beating. Now, because we've talked about the conductivity of skin, we should take a look at the inverse, which is the resistance of skin to conducting current. So unbroken human skin has a resistance of about 10 to the 5 ohms. So what voltages are dangerous to us? We actually have to consider 100 milliamps as our danger zone and calculate what kind of voltage will cause this kind of current to flow through our skin. Knowing that the resistance is 10 to the 5 ohms, the current is 0.1 amps for the danger zone. We multiply the two of these together based off of Ohm's law, and we get 10 kilovolts as the amount of voltage required to achieve this dangerous current. So the only issue is, as you're working, as you go about your day, your skin should be unbroken, but you might sweat more and you might wash your hands. So someone who has wet or sweaty hands is going to have much lower resistance, as well as those with heart conditions. Every person is different. So when asking about the effects of resistance of skin or the effects of the human body on these dangerous thresholds, number one, consider the state of the physical state of the person you're looking at. If the person is already unhealthy, then 100 milliamps might not be the danger zone. It might be less. So it could be 50 to 100 instead of 100 to 200 as a brief guess. So based off of common sense, those with heart conditions will probably be more sensitive to lower currents. Now, taking a look at the resistance of the skin, if someone has just washed their hands or has wet hands, either through sweat or just water, then the resistance is going to be lowered, and therefore the voltage applied to achieve the danger zone is going to be lower. So those are two different aspects to consider when we're talking about how dangerous voltages is and how the human body and how differences just in day-to-day life, as well as the healthy state of the person will change the threshold for any dangerous consequences. So moving on, what makes a dangerous circuit? A dangerous electric circuit, so it's no longer about the human body, it's about the construction of the circuit itself. A dangerous electric circuit must have high voltage and be capable of driving sufficient current. So although a battery car can deliver 300 amps, it can't electrocute you since its 12-volt battery is not going to drive a lot of current through the body. So keep in mind, you need 10,000 volts in order to drive a dangerous current throughout your body. So a car really can't electrocute you since its 12 volts is really not enough. So how can it deliver 300 amps? because the potential difference is the property of 2 points, A and B. Electric shock requires 2 parts of the body to be in contact with conductors at different potentials. So in this case, when you're talking about a dangerous circuit, a car battery is not very dangerous because your 2 parts of your body will not be in contact with the conductor at different potentials. So then we have to move on to what are examples of a dangerous situation and how can we be placed in a dangerous situation. So this happens when the operator of a power tool or an appliance contacts a grounded conductor. So let's say your power tool is plugged in through a 2-wire cord. If a short circuit occurs, the tool is going to be raised above the ground and therefore at a higher potential. And if I am standing on the ground with no protection, then I'm going to potentially receive a lethal shock because the short circuit is going to take place. I'm going to be the grounded component that's lower, and therefore the current is going to travel through the tool to me and straight through to the ground. So that's going to deliver a large current through my body and potentially kill me. So the workaround is to use 3-wire cords, where the 3rd wire is going to run from the exposed metal parts to a grounded wire in the outlet. So that's why there are 2-pronged and 3-pronged cords. So we're going to compare an unsafe situation with a safe situation. This 2-pronged electrical cord and plug, and we're going to use that as an example of an unsafe situation. So we have the ground here, we have a person standing here, and they're using a tool. The tool is plugged into a wall jack, and with a 2-prong plug. So when it's plugged into the wall, if there is a short circuit, then these two really don't work, right? So that means the only place for the charge and the current to go through is going to be through the human body, through exposed metal parts, and then straight down to the ground, because it's always going to want to travel to a lower potential. So the current is going to go up to the tool so that you can use it. It delivers enough power for you to use. If there's a short circuit, the current is no longer going to be able to go back through the wire, but rather any exposed metal parts and through a conductor. So this overall is an unsafe situation. In order to mitigate the situation, you can add a 3rd wire. So a 3rd wire that's just connected to the ground, that just in case of a short circuit, the current does not have to find its way out through exposed metal parts and through an exterior conductor. It can use the conductor within the wire to go back to the ground. So here you have a 3-pronged plug. Same thing, you now have 3 lines. It goes up. There's going to be a neutral ground line that connects the object or the tool from the top to the ground. So that once you have a short circuit in the pink and black lines, then there's going to be an immediate and quick way for the current to flow back to the ground. And that is going to be the safest situation through a 3-prong plug. Now, since we know about the flow of current through different conductors now, we should take a look at the electromotive force. So every electric circuit must have some sort of pump that drives the current. So we have to note that the electrostatic force is going to try to push the current from a higher to a lower potential energy. But the pump must push in the opposite direction. The electromotive force, or EMF, is going to push the current flow from a lower to higher potential. Every complete circuit with a steady current must include a device that provides an EMF, and that device could be a battery, is called the source of the electromotive force. An ideal source of EMF must maintain a constant potential difference between its terminals, like a 12-volt battery, independent of the current through it. So we have to define EMF as the magnitude of this potential difference. Most sources of EMF are going to have 2 terminals for connection to other circuit components. When the source of EMF is connected to an external circuit, the current is going to flow through the circuit, and it's going to go from the EMF's positive terminal to the negative terminal. Now, the energy conversion process in EMF is going to lift the charge against the EMF's internal electric field, and this helps to maintain a fixed position between its terminals. Afterwards, your charge is going to fall through the external circuit. So we're going to go through some examples afterwards, just in case this is a little bit confusing. An ideal battery of an EMF epsilon is going to drive a current through a resistor R. It means that we can write V equals epsilon for the amount of voltage that the electromotive force applies is equal to IR. The only thing is, if you do have a circuit and it has internal resistance, that means we have to consider that in our calculations. Real sources of EMF are not going to behave exactly how we want them to behave, or how we've originally described them. The potential difference across a real source is not going to be equal to EMF. Like in our previous equation, we have to deduct internal resistance from that equation. So the potential difference is going to be the amount supplied by your source of EMF subtracted by the voltage produced by the current and some sort of internal resistance. So we call this terminal voltage with internal resistance. And afterwards, we're just going to go through a couple of examples so that you're familiar with how to apply these equations. Let's take a look at the resistance of a light bulb. We know the voltage of a typical household wiring is given as 120 volts. You've probably seen this before. How much current does a 100-watt light bulb draw? What is the bulb's resistance under these conditions? So first, I have to know what information I'm given. I know V is equal to 120 volts. The power is 100 watts. I know that between the two of these, P is equal to IV as a relationship. So I know that I is equal to P over V. So how much current does the light bulb draw? We can use this to find the current. That's I equals to 100 watts over 120 volts, which is then going to be 0.833 amps. So next, in terms of our givens, we also know that V is equal to IR. So from that, I can say R is equal to V over I. Since I've already solved for I should be able to find the resistance fairly easily. So R is equal to V over I, which is equal to 120 volts over 0.833 amps, and that gives me 144 ohms. So keep in mind, always write down what you're given first and then find the most suitable equation to solve. Okay, so let's take a look at a defective appliance. Let's touch a defective appliance while standing on the ground, and it means you're going to feel a slight tingle of a 2.5 milliamp circuit current. What is your resistance, assuming you're touching the hot side of the 120 volt household wiring? So this question itself, let's just write down what we're given first and then try and figure out what they're asking us to find. So what's given? We're given I is equal to 2.5 milliamps, which is 2.5 times 10 to the negative 3 amps. V is equal to 120 V. We're trying to find the resistance, so we already know that V equals to IR. And so R is equal to V over I. So that seems like what we're supposed to solve for. So let's immediately solve. R is equal to 120 volts over 2.5 times 10 to the negative 3 amps. And that gives us 48,000 ohms as our answer. In problem 7, we're taking a look at ion channels. So an ion channel in a cell membrane carries 2.4 picoamps when it's opened, but it's open only 20% of the time. What is the average current in the channel? If the channel opens for 1.0 milliseconds, how many singly ionized ions will pass through it in this time? So we're going to have to state some knowns here. Given to us, we know that there is some sort of average current that we have to solve for, but the average current is given by delta Q over delta T. And delta Q, we know, is going to be equal to the summation of all individual currents for all individual components over a specific amount of time divided by delta T. This is then equal to the following. And we also know N is equal to delta Q over an electron, or the elementary charge. So in terms of the average current, what can we do to solve for this? It's a summation. So we have I, AV, being equal to 20%. Because it's only open 20% of the time, we have 20% of 2.4 picoamps. Just keep in mind these have cancel each other out effectively. So we're only adding up all of the different currents. So there's only 20% of the original current, 2.4 picoamps, and then you have 80% of 0 picoamps, because there's nothing else. So that's going to give us 0.48 picoamps as the average current within the channel. Now, next we want to solve for how many singly ionized ions pass through it. That's going to be N. N is equal to delta Q over E, which is equal to I delta T over E, which is 2.4 picoamps, 1.0 millisecond, and 1.6 times 10 to the negative 19 coulombs, which is equal to 1.5 times 10 to the 4 singly ionized ions. And that's it. Okay, so in this example, we have a cylindrical resistor that's 5 millimeters in diameter and 1.5 centimeters long. It's made of a composite material whose resistivity varies from one end to the other according to this equation, from 0 to L. And we also are given the constant for resistivity. Now, this is a changing resistivity problem, and we're trying to figure out resistance. If the resistivity keeps changing for wherever the position you're in is, that means that we're going to have to integrate in some form. So we're going to write down what we're given first and see what we have to do to figure out how to go from resistivity to resistance. So we know that R is equal to rho L over A, but if we're taking a look at the total resistance and it's not defined by a uniform resistivity, we do have to have dr is equal to rho x dx divided by A. Now we know rho x is already given to us as rho naught 1 plus x over L, e to the x over L. From 0 to L, we know R is equal to 0.0025 meters. We know L is equal to 0.015 meters. And we know rho naught is equal to 2.41 times 10 to the negative 3 ohm meters. Next, we do want to solve. And we start off with integrating dr from 0 to L. So that would be rho naught 1 plus x over L e to the x over L divided by pi r squared dx. We can factor out the constants, which would be rho naught over pi r squared, and then have the integral from 0 to L of 1 plus x over L e to the x over L dx. Now, how can we make this easier to solve? We can split this up into two integrals. So we have r is equal to rho naught over pi r squared. Then we have the integral from 0 to L of e to the x over L dx, plus the integral from 0 to L of x over L e to the x over L dx. Now, based on what's in the brackets here, we can further simplify this using derivatives. So we know that d over dx of x e to the x over L is equal to e to the x over L plus x over L e to the x over L. So based on that, it should be fairly easy to solve for this integral now. And so we have r is equal to rho naught over pi r squared. And that is simply x e to the x over L from 0 to L. That gives me r is equal to rho naught L e over pi r squared. And that's going to give me 2.41 times 10 to the negative 3 ohm meters. L is, 1.5 centimeters, 0.015 meters. Elementary charge. And then pi, 0.0025 meters squared. And that gives me approximately 5.00 ohms. So now it's time to take a look at DC circuits and how we can analyze circuits. First thing, we have to go through our circuit diagrams. Then we're going to take a look at how we can combine resistors in series and in parallel. We'll only go through this briefly because they're very similar to capacitors in terms of their equations. Then take a look at Kirchhoff's rules and how they apply in circuits, and also how we can measure different quantities within a circuit using measurement tools like ammeters, voltmeters, and multimeters. So, symbols of an electric circuit. An electric circuit has a collection of electrical components connected by conductors. We assume wires are the perfect conductors so that all points are connected at the same potential. Typically, we use the squiggly lines or the zigzag lines for a resistor, the parallel plate capacitor symbol for a capacitor. You have this battery or source of EMF, and for measurements, you have a voltmeter and an ammeter. You can also have a switch and also a ground. We will not really be talking about variable resistors or capacitors or fuses. We will primarily be focusing on the rest. Now, series resistors, or R series, very similar to series capacitors, but opposite. So we have to consider resistors in series is going to be similar to capacitors in parallel. Why is that? So the current through circuit components in series is going to be the same. So we have to find the current and voltage across the resistors. The voltage is VI equals to IRI across each series resistor. So same as capacitors. If you're talking about capacitors in series, the current is going to remain the same. So here we use the same concept. Keeping I constant, you end up with I equals to V over R. So the battery is going to be connected across the series combination. So we have voltage, or E, epsilon, is equal to I times the summation of Ri. Or you have I equals to epsilon over the summation of resistance. So that is what has to remain constant. Now, if we want to calculate the equivalent resistance of resistors in series, we know that the current has to be constant, so that the equivalent resistance would just be the sum of the individual resistances. So R series is simply the summation of your individual resistors. So that's very similar to capacitors in parallel, but this is for resistors in series. So taking a look at the voltage for series resistors, we can calculate the voltage across each resistor because we know we have a current, we have a constant current. So we can use Ohm's law, V equals to I over R, I times R, in conjunction with our original definition of I equals to epsilon over R series. So combining the two of them, we have VI for the individual voltage across the resistor we've chosen is equal to epsilon Ri over R series. So series resistors are called voltage dividers because the battery voltage is going to be divided amongst your resistors and is proportional to their resistance. Now we take a look at parallel resistors, or R parallel. So now we take a look at what happens when the voltage is constant. When the voltage is constant, we are able to find the current across the resistors. So the current is going to be I is equal to epsilon over Ri. So it's the epsilon that stays the same. Because the epsilon stays the same, it means that we can factor it out and we get 1 over Ri. So the total current is going to be I equals to epsilon factored out times the summation of 1 over Ri. This means that we can calculate the equivalent resistance if the resistors are in parallel in a reciprocal fashion. So this looks very similar to equivalent capacitance in series, but this time it's equivalent resistance in parallel. So just keep in mind, we already know the equations for combining capacitors. Combining resistors is pretty much the same, but just reversed. So what are some tips for analyzing circuits? First, we take a look at series and parallel combinations. We're going to solve for equivalent resistance or capacitance. We have to redraw the circuit with equivalents and then repeat number 1 to 3 until a single equivalent remains for each of the resistors and capacitors. Afterwards, when you're asked to evaluate individual quantities, you can just consider how series components will carry the same current as the equivalent, and parallel components, whether it's resistors or capacitors, they're going to carry the same voltage as the equivalent. Sometimes you have to work backwards if required for the question. But in general, the two most important aspects to remember is that if you have a wire coming in and the wire gets split up into different capacitors or resistors, it is going to carry the same voltage because they are parallel components, and then because it's the same voltage going through to all of them and then going out. Now, if you have components in series, the current is flowing through each one separately in a line in a specific order, and so they're going to carry the same current as the equivalent component in series. Now we have to take a look at multi-loop circuits. So circuits are not just as simple as a rectangle. There can be different junction points where conductors or wires connect different regions or provide like a shortcut from one region to the next. So a junction is a point where 3 or more conductors meet. A loop is going to be any closed conducting path. So over here, we take a look at this diagram, and I can count 1, 2 junctions. These are not junctions because there's only two, there's basically one input and one output. For a junction, you need to have at least one input and at least 2 outputs, or vice versa. There has to be 3. So in terms of a loop, I have a closed loop over here, a closed loop over here, and then a closed loop for the whole thing. So how many rectangles or closed loops can you count? We'll take a look at this example. Can you identify the junctions over here? Well, taking a look here, A has 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So there should be 4 junctions in this example. E and F are not junctions because they only connect 2 conducting elements. Now, can we identify the loops? There's the exterior loop, which we'll call number 1, going from the positive end to the negative end in this direction. We have 2 closed off sections here, triangular shapes, so another 2 and 3. And last is this open area here. It's also closed off, and that's our 4th one. So there are 3 closed off loops and 1 exterior loop. Because we can now qualitatively observe what are loops and what are junctions, we can now define 2 different rules that are called Kirchhoff's rules. Charges that move through a circuit are going to gain energy at EMFs and lose energy at resistors or other components. So every time current or charge moves through the loop, it's going to gain and get refreshed each time it passes through the battery or source. And then as it goes through the current or the circuit, then it's going to lose some of that energy and then get revitalized in the next round. So in Kirchhoff's junction rule, the algebraic sum of currents into any junction has to be 0. So basically, every input has to have an equal output, whether it's one input being split into 2 outputs or 2 inputs being combined into 1 output. So the algebraic sum of the currents going in and out must sum to 0. With Kirchhoff's loop rule, the algebraic sum of potential differences in any loop, including those of EMFs and resistive elements, must equal to 0. So if you add up the sum of all of the potentials across all of the components throughout one entire loop, you should have a total sum of 0. So let's take a look at each of these separately. As a visual explanation, I have a junction over here. I have current coming into this junction and another current I2 coming into this junction. Now, leaving this junction is a current that's equivalent to I1 plus I2. So the current leaving the junction has to be equal to the current entering that junction. Loop rule is a little different. It's a little bit more difficult to explain visually. Kirchhoff's loop rule states that the sum of the voltage differences around the loop has to be equal to 0. So to find the sum, a direction of travel has to be chosen. So you get to choose the direction of travel, and you have to be careful with the signs. So over here, you have a positive voltage. The travel direction is from minus to plus. So that means it's going, from plus. It exits from the plus and then goes towards the minus. Or when you're just looking at the battery itself, the source of EMF has charge going from negative to positive terminals. If you have negative epsilon, it means that the travel direction is going to be from the positive to negative terminal. Now, how does this change when we're taking a look at resistors? If for a resistor you have plus IR, the travel is going to be opposite to the direction of the current. If you have negative IR, the travel is going to be in the direction of current. So being able to explain this is important and will most likely be in the next assignment as well, just so you can get some practice in explaining these different rules. So tips for analyzing multi-loop circuits. You have to identify the loops, identify the junctions, and identify the direction of the current. You can use Kirchhoff junction rule to say the current going into the junction is positive and out is negative. You should use Kirchhoff's loop rule to write equations for voltage, and you can either go counterclockwise or clockwise. Usually what I like to do is to say that the voltage change from positive to the negative terminal is plus epsilon. The resistors in the direction of the current will be negative IR. So only focus on what you need, or else you'll end up doing a bunch of redundant calculations that aren't required. Last but not least, we're going to take a look at electrical measurements. There are such things as voltmeters, ammeters, ohmmeters, and multimeters. A voltmeter is going to measure the potential difference. Ammeter, the current, ohmmeter, the resistance, and multimeter is a single instrument that helps you calculate all of these just in one device. So now we want to be able to go through a few practice problems where we're designing circuits as well as analyzing the different circuits. Now let's take a look at designing a voltage divider. So a light bulb with a resistance of 5 ohms is designed to operate at a current of 600 milliamps. To operate this lamp from a 12-volt battery, what resistance should you put in series with it? So we do want a diagram or a circuit diagram just to visualize this. We know there is a battery coming from a 12-volt battery. So we have plus, minus, and this is called 12 volts. There's a light bulb with a resistance, so we use that. And what resistance should we put in series with it? So that is in series. So R1 is equal to unknown. R2 is going to be 5.0 ohms from the light bulb. And there's also a current. The current is given to us. I is equal to 600 milliamps. Now to solve, resistors in series are going to add directly. So that means R equivalent is equal to R1 plus R2. With a steady current, we know that V is equal to IR, which means I is equal to V over R. And that's going to be the equivalent resistance. So how do we solve? First, we should figure out what REQ has to be. So we know REQ is R1 plus R2. We can combine everything together. We have I is equal to V over R1 plus R2. I'm trying to solve for R1, so I'll have to rearrange this. We have IR1 plus IR2 equals to V. Searching for R1. So R1 is going to be V, which is equal to epsilon. We have epsilon minus IR2 divided by I. That gives me R1, 12 volts minus 600 times 10 to the negative 3 amps. R2 is 5.0 ohms divided by 600 times 10 to the negative 3 amps. So R1 is then going to be approximately 15 ohms. So that is the resistance that we would have to put in series with the light bulb to operate the lamp from a 12-volt battery. Problem 10 is a circuit with series and parallel components. We're trying to find the current through a 2-ohm resistor in the following circuit. So where is the 2-ohm resistor? It's right here. We're trying to find the current that flows through that one specifically. So let's just label this. We have R1, we have R2, we have R3, and we have R4. So we're trying to find the equivalent resistance, and we're also going to label this as epsilon. So first step, find Req. There are some in parallel and there are some in series. The first one we're going to start off with is in parallel. So in parallel, it's these two, R2, R4. R2, 4 is equal to 1 over R2 plus 1 over R4. That's going to give basically we have 1 over 2 plus 1 over 4. And that would be 8 over 6 ohms, or 1.33 repeated ohms. Okay, so now we have whatever is in series. Which is then going to be R equivalent is equal to R1 plus R24 plus R3, which is equal to 1 plus 8 over 6 plus 3 ohms, which is 5.33 ohms. Okay, so now we can redraw the circuit. Redraw the condensed circuit with Req. So that means we have battery, which hasn't changed, plus minus. It's still epsilon equals to 12 volts. But we now have an equivalent resistance, Req, equals to 5.33 ohms. And our goal is now to solve and find the current flowing through Req. So it's number 3. Now the current through Req is going to be constant. Req is going to be constant, so V equals to IR. We know I is going to be equal to V over R equivalent. So that means we have 12 volts being distributed through 5.33 ohms of resistance, and that's going to be 2.25 amps. Okay, but that hasn't really solved our problem. We're trying to figure out how much current is going through resistor 2. So we have to be a little bit more specific. We're going to find current through R2. So a current in series, so I'm just going to write this down. A current, bring this down a bit. In series, so that would be R1, R24, and R3 has the same magnitude. So that means R24 has I24 equals to 2.25 amps. Now looking at R24 in parallel, only voltage is uniform. So it means we have V24 is equal to I times R24. So that means we have V24 is equal to 2.25 amps times 1.33 ohms for our equivalent resistance for R24. So that gives us V24 is equal to 3.00 volts. That still doesn't give us the answer. Now we know that V2 must have the same voltage as V24, so it has to be 3.00 volts. And we know that R2 has a resistance of 2 ohms. Now it's between these two, we can say V2 is equal to I2 R2, and I2 is equal to 3.00 volts divided by 2 ohms, which is equal to 1.5 amps. That's flowing through that resistor specifically. Let's take a look at a multi-loop circuit. We're trying to find the current in the resistor 1 ohm of the following circuit. So there's multiple loops happening. It means we're most likely going to have to use Kirchhoff's law. And we want to find the current in resistor 1 ohm. So this, let's just label this first. We're going to call this epsilon 1, and this is going to be epsilon 2. We call this R1. Oops. We call this R2, and then R3. So first, use Kirchhoff's rules. See what we can figure out. We're going to have to label the circuit with junctions and loops. So I'm going to use blue for my junctions. There's going to be one junction here, it's A, another junction here, which we'll call B. In terms of the loops, we're going to use we're going to use purple. So loop number 1, call this L1. Loop number 2, from positive to negative, we have this, so L2. And then the next one, we have L3. We're just going to define this as L3. So there's 3 loops. I'm going to focus on junction first. So let's look at junction A. For junction A, we know that the sum of all currents must be 0. We're going to say there's a current coming from I2, and then it's going to leave towards I1 and I3. So I'm going to have to label the currents now. Looking at the current here, I know current's going to flow from positive to negative, and then it looks like the current's going to go in this way. So this is I2. Now I take a look over here for this loop. I'm just going to assume this goes this way, and I have I3. And then for the next one, I have I1. So overall, it looks like I have I2 plus I3 minus I1 is equal to 0. We're going to call this equation A. Next, we have loop. We're going to use loop 1 for this. And in loop 1, we know that the total sum of the voltages must be equal to 0. So in loop 1, I know I start off with epsilon 1. Then I'm going to lose some voltage with the resistor. So I have minus I1 R1 minus I2 R2 equals to 0. So what that tells me is I have 6 minus 2I1 minus I2 equals to 0. And I'm going to call this equation 1. Now my next loop, I'm going to do loop 2. Once again, sum of the voltages must be 0. In loop 2, I have epsilon 2 plus I3 R3 minus I2 R2 is equal to 0. Now I have to think, why is that? It's because of the way that it's been labeled. I3 is going into the junction A, and that's opposite to the current flow, opposite to the loop. So that's why we have to have plus I3 R3. So that gives us 9 plus 4I3 minus I2 equals to 0. And we're going to label this as equation 2. Now we have to try and find the current in R2. So that involves us combining all of these equations. I'm just going to go to the next slide. And we're going to solve for R2. We want I2 first, so we have to eliminate all the other variables. So we have 6 minus 2I1 minus I2 equals to 0. The second equation was 9 plus 4I3 minus I2 equals to 0. This gives me 2I1 equals to I2 minus 6. I1 is equal to 6 minus I2 over 2. Remember, we're trying to solve for I2, so we want to get rid of I1. And then this one, we want I2, so we're getting rid of I3. Now, from the two of these, we can't really do much with it, but we can use equation A, and hopefully it will help us. So, using equation A, we have minus I1 plus I2 plus I3 equals to 0. I1 is now replaced with I2 minus 6 over 2 plus I2 plus I2 minus 9 over 4 is equal to 0. I can see that I2 is going to be equal to 6 minus I2 over 2 minus I2 minus 9 over 4. I2 is then equal to 3 minus 1/2 I2 minus 1 over 4 I2 plus 9 over 4. Continuing on, I have 1 plus 1/2 plus 1/4. I2 is equal to 3 plus 9 over 4. That gives me 7 over 4. I2 is equal to 21 over 4. And therefore, I2 is then going to be 21 divided by 7, which is 3.0 amps. And that gives me the current that's flowing through the resistor R2. So now that we've learned a little bit about circuits, we want to go through how capacitors work in circuits. So we're going to go through an overview of an RC circuit, what it consists of, and then how a capacitor can be charged and discharged. So quick overview. We're going to introduce capacitors, and that means circuit quantities are going to change more slowly versus instantaneously. Since Q is equal to CV, a change in voltage is going to require a change in charge. And the magnitude of current determines the rate at which the capacitor charge can increase or decrease. Now, that's just a long way of saying we're going to start introducing capacitors to our circuits, and so the circuit quantities are going to change slowly versus instantaneously. So RC circuits are going to be circuits that include both resistors and capacitors. The voltage across a capacitor is not going to be changed instantaneously. There's going to be a moment of charge and a moment of discharge. So because the charge can increase or decrease, we have to look at these two cases separately. So we're going to start with the first case. Before a capacitor can be discharged, it has to be charged. So we're going to take a look at this circuit in a clockwise fashion. So starting from here, the voltage increase of epsilon across a battery, it's going to go through and drop IR of a magnitude of IR across the resistor, and then it's going to drop a further VC equals to Q over C across the capacitor. So therefore, the loop equation is going to be epsilon minus IR minus Q over C should be equal to 0. So that's from Kirchhoff's loop law. We have now two unknown values of I and Q, but they're closely related by the following equation, I equals to dQ over dt. So that means we can rearrange everything. You can replace I with di over dt, and we can replace Q with dQ over dt. And that's going to be equal to 0. So we have two equations. We have I equals to dQ over dt, and we have this. Putting it all together, it gives us the following, and then we can rearrange it to have this di over dt is equal to negative I over RC. But this isn't enough. I still want to figure out the current for the system, so I have to integrate. After integrating, I end up with, you can take a look here, you end up with I is equal to epsilon over R times e to the power of negative t over RC. This over here is considered a time constant. And so it's an exponential time constant, which tells us that there is a correlation between time and current being sent across the circuit. So in terms of the capacitor voltage, we can also calculate that because we know that the voltage is going to be equal to the provided amount from the source minus the voltage from the resistor. So we have VC equals to epsilon minus IR, and IR we know is going to be given by this. So afterwards, we can rearrange and solve for the voltage of the capacitor, which is equal to epsilon times 1 minus that time constant. Now that we have that, we want to take a look at a discharging event. If we connect a charged capacitor across a resistor, the voltage is going to drive a current through the resistor. The current is going to transfer the charge from the positive to the negative capacitor plate. And this is going to lower the charge on the capacitor. And because Q is equal to CV, that means that the voltage on the capacitor will also drop. So over here, you can see that the voltage of the capacitor is connected to the resistor in some fashion, and that the voltage is going to drop. So we're going to reanalyze the loop equation going clockwise again. We now have QC minus IR is equal to 0. We know that the capacitor charge Q is going to be reduced. So this equation is now going to be I equals to negative dQ over dt instead of positive. So similar way of deriving this equation. You don't have to know it, but if we differentiate the new loop equation, we get di over dt equals to negative I over RC. We can then rearrange for I and solve, and we get this, but we can also rearrange and redefine it in terms of voltage to get V naught times e to the power of negative t over RC. So there are two equations to know of that we won't really expect you to apply. The concept is more important. Know about the differences between charging and discharging a capacitor in a circuit, and the fact that there's an exponential dependency on time for each of the voltages. Okay, so now we can actually move on to applications to life and medical physics. We're going to cover three different items today. The Hodgkin-Huxley model for membrane current. We're going to take a look at voltage clamp experiments, specifically for biophysics. And then we're going to take a look at the patch clamp technique. Now, keep in mind, these three are just examples of applications to life and medical physics. As part of your assignment this week, you're going to take a look at different applications of circuits and capacitors, resistors to medical devices. Keep in mind, there are many more applications than what I'm presenting here. These are just ones that I think are more suitable based on the design of the circuit. So the cell membrane. In 1952, Alan Hodgkin and Andrew Huxley developed a circuit model for the cell membrane, and it was great because they won the 1963 Nobel Prize for Physiology and Medicine. Now, the Hodgkin-Huxley model was the first model of a cell that successfully modeled the axon membrane of a giant squid. So that is what they won the Nobel Prize for. And what does this model include? It considers the effects of three batteries, epsilon K, epsilon Na, and epsilon L, to represent the electrochemical effects of potassium, sodium, and L being the other ions within your solution. You then have different resistances. You have K, Na, L for the resistance of the cell membrane to each of these ionic species. And then you have the current for each of these species to represent their flow through the membrane. Now, the Hodgkin-Huxley model of a cell, it first modeled the axon membrane of a giant squid, and in the axons of a neuron, the sodium and potassium channels are going to dominate, and that's why they are here. And all the other ions are just grouped together into just L. The total membrane current is going to be given by the sum of all four currents listed, with the capacitor current equal to I equals to C delta V over delta T from Q equals CV. So, in other words, the total membrane current is going to be defined by the sum of all of these currents. All of the channels for sodium and potassium are going to be voltage gated, so their conductances are going to be varied with time. Note that the voltage Vm is the membrane potential between the inside and the outside of the cell, and there's also a capacitor that causes that time-dependent behavior. So, in terms of understanding this diagram and explaining it, which you'll be asked to do in the assignment, it's important to understand that the capacitance here is going to be the component that gives the circuit its time-dependent behavior. Now, an introduction to some voltage clamping techniques. The electrical properties of individual neurons can be studied in living tissue using inserted microelectrodes. An electrode is a glass capillary tube that contains a conducting salt solution and a metal wire electrode. Electrodes are used to measure the membrane voltage, and they inject small amounts of current so that we can measure and detect the changes being produced by that injection of current. Usually the microelectrode is set to a zero potential in the extracellular fluid, and it reads the resting membrane potential. Now, there are many different ways of reading this voltage and applying this technique. They all have a similar feedback system, and it's a negative feedback system. what I want to say as well is that a basic voltage clamp is going to repeatedly measure the membrane potential and then change the membrane potential to a desired voltage or a desired value by adding the necessary current to restore it to that amount. So this basically clamps your cell membrane or whatever you're looking at to a desired constant voltage, and that's why it's called voltage clamping. It keeps the voltage constant or restores it to that clamped voltage. So your voltage clamp technique should be able to record how much current is delivered to restore the desired voltage. And the various ways of taking this measurement always require a negative feedback system. So that means no matter what technique is being used in the family of voltage clamp techniques, there has to be some sort of feedback amplifier to see how much voltage has been lost and then allow it to generate enough current to restore that voltage. So I just want to go through some basic clamping techniques. Number one, there's the gap method. So in the gap method, there are two insulating dividers that will help with the injected current. In a clamping technique, there's a double electrode. It's used for cells, so there's a cell in the middle. There is an electrode that measures the voltage and an electrode that measures the current, unlike the two dividers from before. Then there's the patch clamping method, in which case you have a membrane patch, and then you have some sort of capillary that sucks up a portion of the membrane over here. You can measure the voltage here, and you can also detect changes within the current. So we're going to focus on that last one, the patch clamp technique. Patch clamping is very common and popular in biophysics. It was developed in the 1970s, and it uses a micron diameter pipette tip. You press that tip against the cell with some suction applied to form a tight seal on your microscopic area, and the resistance between the inside and outside of the solution is in the scale of gigaohms. So this technique has led to a 100-fold increase in the sensitivity of membrane current measurements, which is great for nanotechnology engineering and biophysics applications. So here's a detailed overview of how the patch clamp technique works. From this diagram, I'm going to explain the different steps of the patch clamp technique, which are also stated in the next slide. So the general principle starts from the following. A glass pipette over here contains an electrolyte solution. It's going to attach itself or tightly seal itself onto the cell membrane over here and isolate the membrane patch electrically. So over here, it's electrically isolated. And if you zoom in close enough, there should be a curved area where the membrane has been sucked up into the pipette. Currents are going to flux through the channels in this patch here. In this example, there's only one ion channel. And so the currents will flow into the pipette and can be recorded by the electrode that is within the pipette. And that electrode is connected to a highly sensitive differential amplifier. In the voltage clamp configuration, the current is then injected into the cell through a negative feedback loop to compensate for any changes that are being recorded by the membrane potential. So what we are going to notice is the recording of current. It allows for conclusions about membrane conductance. So as we restore the voltage by introducing and injecting current, knowing how much current is injected will indirectly tell us how well the membrane has been conducting its current. So that's just the overview of steps that I just walked through that you can read yourself as well. Now, what are the different types of patch clamps? Even though a patch clamp technique is a subcategory of the voltage clamping technique, now we have different types of patch clamps as well. There are 4 different recording methods for a patch clamp. There's the cell-attached recording method. So that's when the pipette is in close proximity to the cell membrane and mild suction is applied to gain a tight seal between the pipette and the membrane. There's the whole cell technique over here, where you apply another brief but strong suction, and the membrane actually ruptures over here, and the pipette gains access to the cytoplasm. There's the inside-out method over here. Inside-out method, it's closely related to the cell-attached mode, so over here. But if we start with the cell-attached recording, either the membrane ruptures and we go to whole cell recording, or the membrane does not rupture and you can actually slice the component that has been sucked up and expose the membrane to the air and put it in another solution if you want. So the cytosolic surface of the membrane is exposed. Now, the last one is the outside-out recording. In the whole cell mode over here, if you do end up rupturing the cell membrane and also slicing the two edges of the membrane, you end up with one portion over here that's dangling and another portion here that's dangling. But due to lipid self-assembly, it's most likely going to reconnect, and you can have your own localized area that has been created by your two small pieces of membrane that have reconnected to form a small vesicle. So we consider that the cytosolic side facing the pipette solution. So something important to know and to realize is whether we want to analyze the extracellular component of the cell membrane or the cytosolic side of the cell membrane. If you want to analyze what's happening on the ECF side, then you would probably use cell-attached or inside-out recording. If you want to look at what happens on the inside part of the membrane, the cytosolic side, then you're going to look at whole cell recording, either by rupturing the membrane to gain access to the whole cell on the inside, or you can split it up and create a tiny environment yourself with the cytosolic side. Okay, now for a summary. We're going to go through some key concepts and important equations, primarily important equations. So keep in mind when we're talking about current, there can be steady current, which is the macroscopic view of things, and you can look at the instantaneous current, which gives you the microscopic view of things. Now, if we're taking a look at microscopic current, you end up with current being defined as NAQ VD, where VD is your drift velocity. Very important concept to know. Key equations for current density would be NQ VD, and another view of Ohm's law from the microscopic perspective, J is equal to conductivity multiplied by the electric field, where conductivity is the inverse of resistivity. That means you can have another way of writing Ohm's law with resistivity. And if we did take a look at the steady current, then that means that we have the macroscopic view of Ohm's law, where I is equal to V over R. And then between those two equations, we can create a correlation between resistance and resistivity. So key equations for voltage and current. When working with circuits, we have B equals IR, we have electric power, and we have terminal voltage with internal resistance. We have that comparison chart for Ohm's law. It would be good to go through the microscopic and macroscopic views of each and to note the differences between the two of them. In terms of circuits and components, we found out that the equivalent resistance in series was just the sum total of all individual resistances, and the equivalent resistance for resistors in parallel is the summation of all of the reciprocal resistances. Last couple of slides have to do with circuits and Kirchhoff's rule. Remember Kirchhoff's junction rule, where the sum of the currents into any junction must be equal to 0. And for the loop rule, the sum of all potential differences within the loop must sum up to 0 as well. So as your current or your charge is, as your current gains charge through your source of EMF, it's going to lose its voltage as it goes through each of the components of your circuit. So RC circuit equations and concepts. An RC circuit basically consists of resistors and capacitors. Keep in mind, the capacitor can store energy, but the resistor can control the rate at which it charges and discharges. When you combine the two together, you have a time dependence that can be described by your time constant, RC. So when we're taking a look at equations like this, we know that there's going to be two types. There's going to be one where the RC circuit is going to be charging, and you have an equation where the capacitor is charging and it is equal to this. You also have another equation where the capacitor has to discharge, and the voltage then is proportional to this quantity over here. And that about sums it up for our discussion about resistors, conductivity, resistivity, and circuits.